Okay, so the goal of today's lecture is to try to determine, to even succeed probably, that phase transition is continuous for q smaller or equal to 4. And we are going to change completely. The proof for q very large was combinatorial in nature. Here we are going to use analysis somehow. So in order to study the geometry of these loops, which encode the whole structure of the random cluster model, what we are going to do, we are going to try to select one first. We want to study a loop, so we would like to somehow enforce boundary conditions in such a way that there is a natural selected loop or interface. So I already said something like it was B maybe, so continuous phase transition. And so the first thing I want to discuss is the notion of Dobrushin boundary conditions. So take omega to be a subgraph of Z2. But I'm going to ask this graph, I'm going to ask that it is connected and with connected complements. That's going to be my graph omega. And in this case, we are going to call this type of graph discrete domain, because we think of the discretization of a simply connected domain. We will go back to this later, either today or in the next lecture. So if you look at this guy and you go along the boundary, so this guy looks like that. Maybe it has bridges and things like that. When you go along the boundary, you describe a self-avoiding polygon, except that you can pass several times through the same edge, but on both sides somehow, not on the same side. And what I'm going to assume is I'm going to assume that I can find 2 points A and B on the boundary. So let A and B be on the boundary of omega. And I'm going to call this part of the boundary delta AB and the other part delta BA. So I'm going to call delta AB is a part of the boundary of omega from A to B when going counterclockwise. And same thing, similarly, you can define this thing to be the part from B to A. Okay. So the Dobrushin boundary condition now, they are going to be very simple. They are going to be the boundary condition that you obtain by just wiring the arc BA. So boundary definition, the Dobrushin boundary condition, they are given, if you prefer, the partition function, the partition of the boundary is going to be the arc BA and the singleton X. So it's free on the arc AB and wired on the arc BA. So it's free on AB and wired on BA. So it's not completely clear why this is a nice boundary condition, so let's try to understand why now. Let's do a very simple drawing. Let's say 3 by 1, 3 by 2. This is difficult this morning. And so let's assume that A is here and B is here. So you saw that if you wire the arc, so if you say that these two guys anyway they are wired because they are on this arc, then the state of the edge here is irrelevant, right? It's independent of everything else simply because when I count clusters, the fact that the two endpoints are necessarily connected. So what I'm going to do is I'm going to declare it to be open. So another way of saying is that if I want to enforce wired boundary condition, what I can just say is that the arc is made only of open edges. So let's do that. So these guys, they are automatically open. And maybe there are other open edges. Let's say like that. Now remember that the dual of wired boundary condition is free boundary condition and vice versa. So if I draw the dual of my graph, remember there are edges on every, so the dual of a finite graph is we defined it to be just a set of dual of edges of the dual lattice which correspond to an edge of the original graph, so I get something like that. And here I can look at the boundary condition on this thing. And because I said that the free boundary conditions are dual to the wired one, so here all these guys are closed because these guys are open automatically. But on the other side, somehow, the boundary condition on these vertices is wired because it's a dual of the wired boundary of the free boundary condition on the primal thing. And exactly like I said, I can enforce the wired boundary condition to be just because of open edges here. What I could do to enforce somehow the boundary condition here to be wired is to add these two vertices and to declare all these edges as open in the dual configuration. I didn't change anything to the structure of my graph inside. It just pictorially, it's going to be nicer like that. Now, so let's just finish by drawing the rest of the configuration, which is something like that. And let's draw the loop configuration. So the loop configuration is going to be something like that. Here, remember you have an isolated vertex like that. Something like that. Here we are going to have something like that. And the last one is going to be something that looks like that. I think I never drew something that nice in my life. It's just beautiful, right? I think we should just stop a second to admire it. Okay, good. Wow. Wonderful. Okay, so this is the loop configuration associated to my graph. If you check, the distribution that I started, if I start with the Dobrysin boundary condition, I'm going to also see that this is the distribution on the loop is square root of q to the number of loops. But you notice a huge difference here is that you have loops, but you also have one interface from A to B somehow. Okay, so if I declare, let's say that there is, so if I draw the dual edges, the medial edges, I have a medial edge here, I have a medial edge here. Let's call this edge EB and this edge EA. Okay? So, observation, Dobrysin boundary condition, enforce the existence of an interface, a curve, if you prefer, from EA to EB. And what I'm gonna call this interface the exploration path. The exploration path, and I'm going to denote it gamma, which is in fact a gamma of omega AB of small omega. It depends on all these things. Okay? So this is very good because we exactly isolated one special interface, one special curve, and we are going to be able to study the geometry of this curve. Okay? How do you interpret the loops in this configuration? Well, the loops, they are the interfaces between the medial clusters and the dual clusters, the primal clusters and the dual clusters. So the loops interfaces between primal, or if you prefer clusters, of omega and omega star. What is the exploration path in this case? Well, it's in fact the interface between what? Between the primal cluster connected to the arc AB and the dual cluster connected to the arc. I'm going to give it a name just because it's going to be convenient. I'm going to say delta AB star. Okay? So the interface, the exploration path, gamma, it's the interface between cluster touching the wired arc and the dual cluster touching the free arc in omega star. Okay? Let's try to keep this in mind. It's going to be useful later on. Okay. So why is it good to define this thing? Because now, for those who were there yesterday, Dima defined an observable, something concrete that was defined on the lattice. It was on the hexagonal lattice yesterday. And he proved that it had a limit which was conformally invariant, which was holomorphic. He didn't prove it, but he mentioned it as a theorem. Here, in some sense, we want to see whether we cannot define a discrete observable of my lattice, which, well, if we are very lucky, maybe has an holomorphic limit. So in order to define that, we are going to define something that will be, an observable that will be defined on edges E of the medial graph. So by the way, so we had omega. Now you understand pretty well, I guess, what is omega star, in the sense that you don't need to take these edges into account because, well, they are necessarily close. And you want to add these edges because these edges it's convenient to enforce boundary conditions, to say, okay, to visualize boundary conditions. Now the medial lattice is just, the medial graph omega delta, a diamond, is just going to be all the medial edges which are associated, which are between centers of edges of either omega or omega star. So the medial obtained by taking edges of the medial lattice between mid edges of omega and omega star. Okay. So we have basically everything we want. Now we can define the observable. So, definition. And this definition goes back to several people, to Cardy, to Smirnov, in the generality I'm going to mention. But it already appeared, I think, in Kadanov in some more specific context. And in fact, a lot in conformal field theory, but somehow not under this name, and definitely maybe not with the same perspective. So I think it's fair to say that it was reintroduced by Cardy and Smirnov, and that they were the first one to actually notice really the connection to the lattice models, like what you could do with it. So the definition is the following. So you give yourself a domain, and the observable at a mid-edge E, and you take an edge in the, so an edge of the medial lattice, of the medial graph. And the observable at an edge is going to be something that depends on omega A, B, P, Q, and the edge E. And it's going to be, it's almost, no, that's a bad idea. I'm going to write it here. This is is maybe the most important definition in the whole class, so let's make it big. So it's going to be almost the indicator, I mean the probability is that E belongs to gamma. That the edge that I'm looking at belongs to the exploration path. Except that there's going to be an additional term, which is going to be E to the I sigma times the winding of the curve between E and EB. So let me define and let me explain all these terms. So first thing, what is that? Where we have a few things. So phi AB omega PQ. This is just the measure on omega AB with Duminil-Copin boundary condition. Okay? So from now on, the Duminil-Copin boundary condition, I'm just going to denote them by A, comma B. Sigma, well, sigma satisfies the following equation. That's sine of sigma pi over 2 equal to square root q over 2. And the last thing, I need to tell you what is this W gamma EB. It's called the winding of the curve gamma between E and EB. So what is the winding? It's simply the number of left turns minus the number of right turns times pi over 2. So it's the total rotation that your curve does between E and EB. So c'est-à-dire W gamma E EB, it's pi over 2 times number of left minus number of right turns between E and EB. So you just count how many terms you do left, you subtract the number of terms you do right, and you get the winding, and you multiply by pi over 2, you get the winding between an edge E and an edge EB. So for instance, if I take this edge here, I have two turns on the right, two turns on the left, so I get a winding of 0. I get this guy here. If you check, you are going to have well, 2 turns on the left, and you are going to have 4 turns on the right, or something like this. 1, 2, yeah, something like that. So your 3 turns on the right. So you are going to have the winding is going to be minus pi over 2 in this case, and so on. For a certain edge, you can have different windings. Okay, if you have an edge like that, E, and you try to finish at EB. If you do like that, you are going to have a winding, or even you can imagine doing things like that. You are going to have a winding of pi, of 0. You could also imagine you are going to do something like that. And here the winding is going to be 2 pi, for instance, 4 pi. Okay? So even for a prescribed edge, E, this is a random variable. It depends on gamma. Okay? So this is the definition of the observable. Do you have questions at this point on this definition? Is it clear for everybody what the winding is? This is really the most important definition at this point. So here it's not really, I mean, this sigma, it's a little bit strange, right, that you define this. By the way, I would bet that the most natural thing that you would imagine would be actually to try to prove, to just ignore the red term. I'm going to call this a winding term, because just by habits. This is a winding term. So the most natural thing would be to try to just avoid using the winding term. You just take sigma equals 0, and you just get the probability that the edge is in gamma. And this, if you could understand this, would be very good, because it would basically tell you what is the geometry of the path gamma. The problem is that this observable, if you set sigma equals 0, has basically no nice properties. You don't know how to compute it. You don't know how to, it's not tractable somehow. So you will tell me, okay, but it looks even less tractable if I add this winding term like that, because now I'm even, there are cancellations due to this winding term, which take complex values. Before it was a nice real positive observable without this winding term. Well, you are right, but at the same time, this observable satisfies the following theorem, and that's going to be the main tool that we are going to use. So theorem is that let omega A be, and P equal PC of Q, then for any discrete and contour C, we have that the integral along the contour C of f of z dz is equal to 0. So I need to tell you what a discrete contour is. Well, it's the most natural discretization of just a circuit in R2, in C. This is just a discrete version of contour integrals in complex analysis. So how will you do that? Well, you would do that as follows. So in discrete analysis, when you define, for instance, the gradient of a function, usually you are going to define it on the dual graph. There is something like that, that when you differentiate, the natural space on which your differential of a discrete function lives, so discrete function meaning a function on the graph, is going to be on the dual graph. And it's the same thing for the primitive. So somehow you should really think there is some kind of duality when you define the primitive or the derivative, you pass to the dual of your graph. So here, the contour is going to be something defined on the dual of the graph. You have to trust me on this. So what is going to be, it's going to be just, so remember, we have a dual lattice like that. And remember that the observable is defined on this dual lattice. It's not defined on the primal graph or the dual graph. It's defined on the medial graph. Good. So I'm going to define the primitive, the discrete contour, on the dual of this graph. So the dual of this graph is just made of what? The vertices are exactly the centers of the faces of my graph. I'm going to include also the exterior faces. So it's simply what? It's simply the vertices of my dual graph are just vertices of either the primal or the dual lattice. Okay? So omega, if I look at V of the dual of the medial graph, it's just V of omega union V of omega star. Okay? And circuit is just going to be a sequence of neighboring, a self-avoiding polygon, if you prefer, of neighboring vertices of this dual graph. So it's going to be something like that, for instance. This is going to be this is a circuit. Okay? So a circuit C is a self-avoiding polygon. Let's call it Zi for I equals 0 to n. So because it's self-avoiding polygon Zn is Z0. Okay. I'm going to take this convention on omega diamond star. And then what I mean by the integral, the contour integral on C of f of z dz is just going to be the sum for I equals 0 to n minus 1 of zi plus 1 minus zi seen as complex numbers. So it's exactly what you want to do. You want to say, what is the integral along this path, the path between zi and zi plus 1? I want to say it's zi plus 1 minus zi times the value of the observable here. So times f of zi plus 1 star. So I take the edge zi plus 1, which is an edge on the dual of the Meteor graph. It crosses a single edge of the Meteor graph that I call zi plus 1 star. And the value of the integral along this edge, I'm just saying it's the value of the observable here times zi plus 1 minus zi. If you think about it, that's a very natural thing. If you take a continuous function, or a sequence of continuous function, and you look at this discrete integral and you assume that the sequence of continuous function converge to a certain function, then the discrete contour integral are going to converge to their continuous counterparts with this definition. Okay, so it's a very, very natural definition. And what I'm saying is that if I go at PC, if I go at P equal PC of Q, and if I set, actually I don't need to. If I go at P equal PC of Q, I have this. So you see there is something very strange. Like if I choose this sigma, and I set P equal PC, then I have this property that whatever the discrete contour I take, I get integral equals 0. And here you should think, what are the continuous functions of the complex variable which satisfy these properties that the discrete contour integral vanish? Well, these are exactly the holomorphic functions. So this is some kind of discrete version of Morera's theorem. It's not a version of Morera's theorem, but of Morera's characterization, let's say, of holomorphic functions. In fact, one should be a little bit careful when drawing such a parallel, because here, f should not be seen as a discrete version of a holomorphic function, but rather as a discrete version of a form, in fact. But I don't want to enter into details, but then this would correspond to the fact that the form is closed. So it's not completely what we want, but it's not very far. Yeah?
In the definition of f, you have a gamma, and here in f here is also gamma is...
Yeah, but you see the gamma is integrated out. So gamma is a random variable, and the f, in some sense, is just the average of a certain random variable defined from gamma. But otherwise, gamma doesn't appear in the dependency in f, because that's the average on something depending on gamma. So this is the first thing I want to say. The second thing I want to say is that why is it very good that it looks like the discretization of a holomorphic function? It's very good because the holomorphic functions, they have a property, which is that they are determined somehow by their boundary conditions. In the sense that if you take a domain and say you fix what we call Dobrushin boundary conditions, so you fix the value of your function on the boundary, then there is a unique holomorphic map inside the domain which has these boundary conditions, which is continuous and has these boundary conditions. Okay? This is the Dirichlet principle. And you can also I mean, this is, sorry, the solution to the Dirichlet boundary value problem. And you can do that with more complicated boundary conditions. You can use Riemann boundary condition, Neumann, so Riemann-Hilbert, Neumann, etc. So for instance, instead of fixing the value of the observable, you can fix its derivative or its orientation with respect to the normal vector, things like that. You can do a bunch of boundary conditions and say, well, if I give you this boundary condition, you can give me the unique holomorphic map that has this boundary condition. So this, if you would have a discrete analog of this, would be very nice. Imagine you have a function that you know is the unique solution to a certain boundary value problem on my domain omega. And imagine I give you the fact that I know the boundary conditions. Then you would be able to tell me, okay, well, I know that, I mean, if you give me only the boundary condition and the fact that it satisfies this kind of uniqueness of the solution, then I can reconstruct the observable F. Now, if I have a sequence of domain converging to a continuous domain and a sequence of boundary conditions converging to a certain continuous boundary condition, then if I have every single time a unique solution, when I'm going to take the limit, this unique solution, this family of unique solutions, they are going to converge to the unique solution of the continuous boundary value problem. That's something natural to expect. It's not at all trivial to prove, but it's natural to expect. So it would be wonderful. I'm not going to tell you more about that now. I will tell you a little bit more next time. But it would be wonderful if actually this condition here, that every single contour integral vanish, is actually determining the observable F from the boundary condition. The problem is that you can very quickly convince yourself that it's not the case. So let's try to do that. Observe that in order to have that the discrete contour integral vanish, it's in fact sufficient to have it for the smallest contour you can imagine, so for all the contours that just go around the face. Take a contour going around the face like that. If this contour vanishes for every contour, then any contour is going to vanish simply because a contour in general, if you take a contour like that, well, let's make it a little bit more. A contour like that, when I integrate along this contour, it's exactly the same thing as summing the integral along this contour plus this one, etc., etc. It's the same as summing over all the small squared contours. Why? Because on the boundary here, you are going to exactly get what you want every single time. And inside, well, inside you have, once this guy is counted in this direction, so I get a zi plus 1 minus zi times the f of the observable. But for the other contour, it's counted in the other direction. So I'm going to get a zi minus zi plus 1 times f of the value. Okay? So all the values inside are going to just cancel. So this property I could have restated in a very similar way by just, it just means that the observable, I mean, that the discrete contour along small guys is 0. So the property equivalent to the integral along this contour of f of e dE equals 0 for every face f of omega diamond, maybe star. No, for every face of omega diamond. Okay? Okay. So I just realized that how did I do? No, that's okay. Just this drawing was bad. I was thinking, okay, this drawing is bad. Here I drew a contour on my on the medial graph. Okay, I feel much better right now. This is a discrete contour. Okay. Good. So it's indeed the face of the dual lattice, of the dual of the medial graph. But how many faces do I have? Well, I have one face per vertex of the original lattice. So I have the number of equations is simply the cardinality of this. Okay, the number of vertices of the medial lattice. The number of unknown, if you want, if you would like to reconstruct from the boundaries, the number of unknown is the number of edges I need for every edge to determine the observable. And maybe minus the number of edges on the boundary. But whatever, for generic domains, this thing is twice bigger than this one. There are twice more edges than vertices. So the linear system, if I want to reconstruct the linear system, is underdetermined. Underdetermined. And this is a big problem. Actually, it was such a big problem that at the beginning with stats, we thought that, well, if we cannot get more than that, this is not determining anything. This property is not telling us anything on the model. And we are going to see that, in fact, we can extract, by a small trick, we can extract this information. I mean, still some information. I would also like to say that in the original article of stats, this property was written in the way I'm going to write it in a minute. So there was, I mean, he didn't interpret this, he didn't need to do it, to interpret it in terms of discrete contour integral. And you are going to see that this is exactly what is going to be useful for us, to extract information despite the fact that we don't have enough information a priori. Okay, let me try to prove this theorem. So as we said, it's sufficient to prove this thing. Okay, for any face of the dual of the medial lattice, you have integral equals 0. But if you think about it, this is exactly equivalent to the following lemma, that for every vertex of the medial lattice, if A, B, C, and D are the medial edges around V, say indexed in counterclockwise, edges around V, indexed in counterclockwise order, then f of A, so let's say, let me maybe draw them. So let's say this is A, B, C, or A, B, C, D. Then f of A minus f of C is equal to I times f of D minus f of B. Why is it exactly equivalent? Because up to a complex number, this minus this is exactly the discrete contour integral. No, it's this value times the value here plus I times this value times the value. I mean, it's this value plus I times this value plus I squared, so minus 1 times this value plus I cubed times this value. This is, and if you think it gives you exactly that. So we need to prove that. Just to throw a big word before I do the proof, in order to remember this equation, you have a trick, which is the following. Divide by I. It gives you f of I minus f of C divided by I equal f of D minus f of B. F of D minus f of B, if you look in that direction, it's just, let's say it's the derivative in that direction. It's f of D minus f of B divided by d minus b. So the derivative here should be f of a minus f of c divided by a minus c. A minus c is I times b minus d, d minus b. So this divided by I equals this is exactly a discretization of Cauchy-Riemann's equations. The fact that the x derivative for an holomorphic function is equal to the y derivative of the point. It's exactly that. So f of c minus f of c, f of a minus f of c divided by I equal f of d minus f of b. And now you see actually, when you look at it like that, you see what is the information missing. So you have somehow the Cauchy-Riemann equations around the face of the medial lattice. In fact, what you of the dual of the medial lattice, if you would like to have a nice, but this is just for those who understand, for others it's okay. If you would like to have a nice notion of holomorphic function, discrete holomorphicity, you would need, in fact, the Cauchy-Riemann around faces of the primal lattice as well. So the other half of the information that we are missing are exactly the discrete Riemann equations around the faces of the medial lattice, and not the dual of the medial lattice. So we have half the information because we have half the Cauchy-Riemann equations. Okay, maybe we do an early break. We start at 12 and we prove this and start to discuss a little bit the proof of the continuity of the phase transition. Okay, so let's prove this. So before, let's say that if I take an edge E, okay, which is in the set ABCD, I'm going to call E of omega. It's going to be the contribution. You can see that as a big sum, okay? Subtract the thing and say I want to prove this equals 0. This is a huge sum on all configurations, omega, of the contribution of, of the edge A to f of, omega to f of A, omega to f of C, etc., etc. So for an edge E, E of omega is going to be the contribution of the edge, of the configuration omega to f of E. So what is it exactly? E of omega is by definition, well, first it's going to be 0 if gamma is not in E. That gamma of omega is not in E. Then there are going to be the e to the I sigma winding of the curve gamma of omega between E and EB. And there is going to be the probability of the configuration omega, which this I'm going to call it P of omega just to simplify the notation. So this is a huge sum over all the omegas. There are many configurations of these contributions. And what would be perfect, we have a huge sum. What would be perfect is that for every omega, A of omega minus C of omega minus I of D of omega plus I of B of omega would be equal to 0. This would be optimal because then if you sum over every omega, you are going to, of course, get 0. I mean, it sounds overly optimistic, right? Because that would mean that, in fact, your observable, the cancellations are for every single configuration. And indeed, it is overly optimistic. But what is amazing is that it is overly optimistic by a very little, in the sense that the second simplest thing you can ask is actually working. So what you can ask is that you can pair configurations in such a way that the sum of the contribution is equal to 0. And this is going to be possible, which is something which is kind of amazing.
So the first version,
yeah.
Gamma omega.
That was the opposite. Thank you. E doesn't belong to gamma of omega. Belongs to gamma of omega. Okay, that was wrong on every single aspect. Mathematics and okay. So what we are going to do, we are going to introduce. So we have the vertex V. Notice that the vertex V is either, there are two possibilities. Either the primal graph is like that, and we have the dual graph here, or the opposite. So either you are in the middle of a horizontal or a vertical edge. Let's assume without loss of generality, it's exactly the same proof that it is in the middle of a vertical one, horizontal one. And let's just look at the transformation S, it's an evolution, which map omega to S of omega, which is just omega except the edge crossing V has opposite type. Is switch. Let's put it like that. Is switch. So if it was open in omega, it's closed in S of omega, and vice versa. That's just that. Everything else you don't change. So it's an evolution. And what we are going to prove, let us prove that for any omega, in fact, we have that A of omega plus, minus, or let's say plus A of S of omega minus C of omega minus C of S of omega plus blah, blah, blah equals 0. So you look at the contribution of omega to this. You add the contribution of S of omega, you get 0. Because S is an involution, this implies automatically that the huge sum is equal to 0. Because you can always pair one guy with its neighbor. Or another way to say that, to see that is that if you look at this big sum, it's 1/2 of the sum over omega plus the sum over S of omega. Okay? So this is sufficient to prove that this fix cancel for every omega. So there are going to be 3 cases. So case 1 is simply gamma does not go through any edge incident to V. So we are somehow in this context where through this thing you have either one loop or maybe 2 if these 2 guys are different. So maybe it looks like that. Okay? But the exploration path is going somewhere else. You see that if you switch the state of the edge, the exploration path is not going to go through the vertex V either. So in both cases, for omega and for S of omega, every single contribution is 0 because of this term. So here you get 0, you get, E of omega equal E of S of omega equals 0 for every E in A, B, C, D. And therefore, we have the case 2 is that it visits, say, in omega, the expression path visits 2 edges. And let's, without loss of generality, let's assume it enters through A. And then it has to exit, if it enters through A, the orientation of the path is such that it has to exit through B or through D. Let's assume it goes through B, sorry. So gamma passes through 2 edges, entering at A, say, at A, and exiting at B. So we are like that. This is the exploration path, and here we have a loop. So notice that in S, this is omega. In S of omega, in this case, what I'm going to see that the exploration path goes through the 4 edges in this context. And therefore, case 3 is going to simply be when gamma goes through 4 edges, but this is the same as case 2, because it's just switching the role of omega and S of omega. So in fact, this is the only case we need to treat. So in this case, we need to see that the sum of the contribution is 0. So what I'm going to do, I'm going to take A, B, C, and D. I'm going to look at omega and S of omega, and I'm going to look at the contributions. I'm not all going to express them in terms of A of omega. I'm not going to compute A of omega. I'm just going to express all the others in terms of A of omega. So for instance, for omega, C of omega is equal to what? Well, the exploration path doesn't go through C, so this is 0. And D of omega, same thing. Now, B of omega, how can I express B of omega in this context? Well, A of omega is composed, B of omega is the probability of the configuration, which is the same as the one involved in A of omega. The indicator is 1 in both cases. The only difference is that the winding term is different. Because now I'm looking at, for A of omega, I'm looking at the winding from A to the end. And in the second case, from B to the end. If I look at the number of left turns minus the number of right turns, if I am at A and if I count the same thing at B I have one less right turn than at B, than at A. Whoa, that was difficult. Okay? So the winding is what? It's the winding plus pi over 2. So the winding at B is the winding at A plus pi over 2 because I have one less right turn. So here, if I look at the structure here, I'm just going to be that it's going to see that it's e to the I sigma pi over 2 times A of omega. And that's all. Now, A of S of omega. Notice that the winding, even though the curve changed, the winding didn't. The number of left turn minus number of right turns, if I do like that and then I do something, or if I do like that and then I do something, is the same. Okay? Because the winding between this and this is anyway, whatever the curve here is going to anyway be the same as just, it's going to be minus pi over 2. So the winding term is the same. The indicator is still 1, but this changed. The probability changed. Why? Because now I have one less loop. I didn't prove it, but I told you that the loop representation in this context, you get the same law as before, so you get the square root of q to the number of loops. So the probability of S of omega is going to be the probability of omega divided by square root q. So here, I'm going to just get this quantity. Here, I can check that the winding is not going to change also, so it's going to be this quantity. And now I have these two terms. Here, this term, just it has 1 pi over 2 turn on the left less than before. So it's going to be e to the minus I sigma pi over 2 A of omega over square root q. And here it's going to be e to the I sigma pi A of omega over square root q. You can check because there is one less left turn than here. So I expressed everything in terms of A of omega, and now I just have to sum everybody. So I do the right linear combination, and I using the fact that e to the I sigma pi over 2 minus e to the minus I sigma pi over 2 is equal to I square root q. This was exactly the assumption that sine of pi over 2 sigma is equal to square root q over 2. When you do the sum, you see that it equals 0. So let's say this is star. Star equals 0. So star is satisfied in this case. In case 3, we say that it was exactly the same. So case 3 works the same. Same as case 2. Or if you want, just apply S of omega. Apply S. Okay. So this is the proof. That's my favorite way of looking at it. Stas presented in a different way, which I like also. But so you can look at the original article. It's exactly the same proof, right? But he has a slightly different twist on his vision, which is very interesting as well. But you see, it's very simple. It's completely elementary combinatorics. Okay, so we have our theorem, and now the only thing we need to prove is that the phase transition is continuous. Okay, we are going to go slowly, especially that we have some time. And the first restriction I'm going to make, and it's going to be important, you're going to see why, I hope I will have time to present why, is that I'm going to assume that q is smaller or equal to 2. And in fact, I'm going to only prove it in this context. So proof of a continuity of phase transition for q smaller or equal to 2. So we know that if we take the observable, it doesn't determine, I mean, the discrete contour integrals do not determine the observable, but I can choose a nice domain, choose a nice contour, and maybe with a little bit of luck, this contour is going to exactly give trivial information on my graph, on my phase transition. And it's exactly what is going to happen. So the domain, I'm going to make it a big picture, is going to be etc., etc. So it's going to be a box. I'm going to switch just for, I mean, because it's going to be much more practical, I rotate the lattice. So this is Z2. Okay, just rotate it. And I take a box like that. I'm sorry, I'm going to take a little bit of time drawing this because it's going to make the things much simpler if I manage to draw it, which is not okay. And if I draw it a little bit properly. Okay, that's the ugliest drawing you could imagine, but that's okay. So this is going to be 0. I mean, and, oh, sorry. So this is going to be 0. And let's say this is n0, and this is minus n0, and this is minus n, and this is n minus n. Okay? So it's kind of a half box on the bottom. And let's, because it's not going to help us so much, let's erase everything inside. Okay. Now I draw the medial lattice. And the medial lattice is going to look like that, right? Etc. And I need to tell you what is A and B to apply our theory. And A and B, I'm going to choose A and B to simply be 0 and 0. So let's fix. So omega is this box, which I'm going to call Rn, say. This is Rn. And A is equal to B is equal to 0. So what are the Dobrushin boundary conditions in this context? It means I'm wiring the arc between B and A. But B and A are 0. So I'm just wiring one vertex. I'm not doing anything. So the Dobrushin boundary condition in this context is simply what? Simply the free boundary conditions. So Dobrushin boundary condition in Rn 0, 0 are simply the free boundary conditions. Okay, what is the exploration path then in this case? Well, the exploration path is just what you obtain. So there is an edge entering like that and an edge exiting like that. It's just the loop going around the edge 0, around the vertex 0. This is my exploration path gamma. So I can define the observable. And now I need to tell you what is the contour. So F is well defined. And gamma is the loop around 0. And now I need to tell you the contour C. And C, I'm going to take the exterior, the exterior boundary. This is not a good name, actually. I don't know. But it's this guy. I'm going to just take the simplest you can imagine somehow the exterior contour like that. Okay, so it goes like that, say. So it crosses all the boundary edges. So this is going to be C. And what I'm going to do is I'm going to divide C into several pieces. I'm going to say, okay, there is this piece, so this edge here and this edge here. So this is going to be C0. Then there is going to be the piece of the path there and there. So it's going to be C1 plus and C1 minus. And then there's going to be everything else, which I'm going to call C2. Okay? So C2 is really all the other edges. Okay, so we get that the integral of f of z dz around C is equal to 0, which I can rewrite with my notation of C0, C1 plus, and C2 plus as follows. I can just say, okay, the integral along C2 of f of z dz is equal, or minus this integral, is equal simply to what I get at the top. So at the top, because zi plus 1 minus zi is always 1, it's just the sum of the observable around the edges there. So it's going to be the sum over, actually at the top, let's really say that the edges, I mean, this C0 is actually the edges really of the medial lattice, let's say. So it's the sum over E in C0 of f of E plus the sum over E in C1 plus union C1 minus of f of E. This is an equality, okay? And here the only thing I use is that on the top, zi plus 1 minus zi is 1. Okay, my goal is to try to prove two things. To estimate this in terms of really a property of my original lattice, so original random cluster model, and then to prove that this is not too small. So let me start by this, maybe. So take the absolute value of this. So first, the absolute value of this guy. Well, by definition, this is smaller than the sum over all the edges, all these guys, of zi plus 1 minus zi times the value of the observable here. Zi plus 1 minus zi is always square root 2. Actually, I said 1 because I'm rotating. And so here, let's just say the rotation of pi over 4 times square root 2 z2. Just that every edge of the medial lattice is actually of length 1. Okay? Or otherwise, or no, maybe that's going to be more confusing than anything. Here, let's just put square root 2. So if I do that, the square root 2 times zi plus 1 minus zi is just 1. Okay? So I just have, this is smaller than the sum over the edges on C2 of absolute value of f of E. Now, now what is f of E on the boundary? And that's going to be the trick. I mean, the observation that somehow unfolded everything. Take an edge on the boundary. Let's say this edge. What is the winding? What can be the winding of the curve between this edge and this edge? This is EB, right? This is EB, this is EA. What is the winding between this edge and this edge? Well, whatever the path between this edge and this edge, you can imagine any end of the exploration path, the winding is always going to be pi over 2. You can check. Why? Because you cannot wind outside of your domain. So any curve from here to here, because that's 2 points on the boundary, is going to have the same winding as this nice curve like that, which has exactly winding pi over 2. So in this context, the winding on the boundary is deterministic. In particular, when you take the absolute value, you get 1. So this guy here is always going to be equal. And in fact, anyway, we needed only a lower bound, but we are going to use this observation at another place. It's always equal to this thing. Always. There is only the term, the probability that E belongs to gamma. Now, what does it mean that this edge is on gamma? Well, that means that necessarily here the cluster, the cluster of 0 in the random cluster has to go through this vertex. That's equivalent. You can check if there is a cluster from 0 to this vertex, then the exploration path has to go through this guy. Notice that it could also, the cluster can do like that. It's also possible. But then in this case, the path is going to go like that and then like that. But it's necessarily going to go through this edge. Actually, it's necessarily going to go also through this edge. What I'm doing for this edge is the same for the other edge. So here, when I sum over all the edges, what do I get? I get twice the sum over every vertex on the boundary, the probability that this vertex is connected to 0 in the random cluster model. And here I could have put 0, because these are the free boundary conditions. So this is just twice the sum over x on the boundary of Rn intersected with the boundary of the box of size n. Okay? So just the guys that are far away, not the guys on this thing, but all the guys that are far away, of, actually it's a rotated version of lambda n, whatever, of omega 0, PC, Rn, this is Rn also everywhere for omega here, it's Rn, PCQ, of 0 connected to x. But now, just apply boundary, comparison between boundary conditions and the fact that you have less vertices on lambda n, on Rn than on lambda n, on the boundary of Rn than boundary of lambda n. This is smaller or equal to twice the sum over x on the boundary of the box of psi lambda n of phi 0 PCQ of 0 connected to x. So what did I do? I pushed the Rn to infinity, and I just removed the condition that the x has to be on Rn, on the boundary of Rn, and I keep only that. Now, and this is just going to be a parenthesis here. Imagine I can prove that the absolute value of the right-hand side is bounded away from 0 uniformly in n. Let's assume I can do that. Then, when I'm summing over n, this term would be larger than a constant. If I sum on every x, on every n, I get that the susceptibility is infinite. This was condition P3. So summing, assume larger than a constant depending on q larger than 0, by summing on n, we will get that the sum over all the x in Z2 of phi 0 PCQ is infinite. I'm just summing something which is constant. And this is condition P3. So in this case, I get that I have a continuous phase transition. So the only thing I need to prove is I need to be able to show that the second term is big. in absolute value. Okay. So in the second term, let's start by what is simple. Let's start with this term. This term here is very easy, right? Because we have two. So the integral, the sum of f of e is just f of ea plus f of eb. So f of eb is equal to what? So notice that for ea and eb, the expression path necessarily goes through these vertices. Okay? So the only thing I need to control is the winding. So f of eb, for instance, by definition, is equal to 1. Why? Because the winding between eb and eb is 0. So this guy is always on the curve and has always winding 0. So this is 1. And this guy, well, it's almost 1. It's just that the winding term is pi in this case. So here I get e to the I sigma pi. So I get e to the I sigma pi over 2 times 2 cos of sigma pi over 2. Okay, this is going to be my first guy. Now let's look at the second sum. And I'm going to do a little bit the same reasoning as here. I'm going to compare to the probability of being connected for these vertices, really the vertices on the boundary. So here, notice that for any vertex on the boundary here, you had two edges to take into account, which were associated to this edge, to this vertex. Here is the same. This vertex has two edges which are bordering it. But what I'm going to do, I'm going to, in fact, also observe that the probability that 0 is connected to x is the same as the probability that 0 is connected to minus x. Okay? So I'm going to express this as a sum over the x's here of 4 contributions, 4 edges. These two edges and these two edges. So I'm going to write it as a sum over x on the right. And I'm going to have, okay, let me erase all of this. I'm going to have f of e1x plus f of e2x plus f of e3x plus f of e4x, which are the 4 guys contributing to x. I mean, bordering x or minus x. And by definition, this is going to be, well, everything is going to be expressed in terms of 0 connected to x. And the only thing I need to determine is the winding term. So before, I didn't care so much about what was the winding, because just I was bounding it anyway by 1, by taking the absolute value. Here, I really want to have all the windings. So first guy, this guy, what is its winding? Well, its winding is 1. Its winding term is 1. The winding is 0. Okay? So I get 1. The second guy here needs to do 2 turns on the left to get to EB. So its winding term is E to the minus I sigma pi. Then we have 2 more terms. This guy here has a winding of pi because he needs to do 2 left turns. And the last guy is going to have a winding of 2 pi. It needs really to go around to go to EB. Okay. And so here, let's express everything in terms of e to the I sigma pi over 2. So we have this term. We have the sum over x on the right. Times the sum over x on the right. And here, we are going to get something like, so we are going to associate this guy with this guy, and this guy with this guy, because you see that then it's both terms have an argument of e to the I sigma pi over 2. And it's going to be something like twice, so let's put a 2 here. We are going to get a cos of sigma pi over 2 times cos, plus cos of sigma, and we get 3 pi over 2. Okay? Actually, let me do it a little bit differently, maybe. That was not the, whatever. It's okay. What is important now? Here, so we only care about the absolute value. Okay, so let's take the absolute value. This term and this term, they are the same in the thing. So we get twice the cos of sigma pi over 2 plus this term. Cos of sigma pi over 2 is going to be positive. For q, in fact, any q smaller or equal to 4, sigma is going to be smaller or equal to 1. So cos of sigma pi over 2 is positive. The question is whether this term is positive or not. And basic trigonometry tells you this term is positive if sigma is smaller or equal to a half. So we get cos, so we get this term plus a term which is going to be positive if only, so if sigma is smaller or equal to a half, then the second term is larger or equal to 0. And I do not care about the value of this thing. This is irrelevant for me. The only thing I need is that this term is going to be positive. Okay? It's larger sine of the sine of 1. Yes. Okay. So it's going to be positive, and therefore, indeed, when I take the sum over, the sum for x on the boundary of lambda n of phi 0 pc q 0 connected to x, I had the twice here, which is going to cancel with these 2 here, and I'm going to get that this is larger than cos of sigma pi over 2. So I have a bound which is uniform in n. So when I sum that, I get infinity. And the only thing that I use is this. That this term is positive. But notice that this term really becomes negative for sigma larger than a half. And of course, sorry, I didn't say, q equal 2 exactly corresponds to sigma equal a half. Okay, so indeed q smaller or equal to 2 corresponds to the fact that this thing is positive. Okay, so now for q larger than 2, we are facing a problem with the strategy. Because the strategy, here if we get a negative sign, then it could be that this big sum here is basically tending to cos sigma pi over 2. Oh, bless you. So it could converge to that, and therefore this plus this could actually tend to 0. Maybe it doesn't, but maybe it does. So a natural thing to ask at this point is, when I look at this quantity on x, which is, so for instance, if I look at the sum of the probabilities of being connected to a boundary point like that, if I ignore these guys, I just look at the guys that are far away, is this guy indeed remaining bounded away from 0 or not? If it remains bounded away from 0, that means, okay, maybe just our method is not the right one. We need to be a little bit more delicate with this sum, and maybe we can still do it for q larger than 2. But if it tends to 0, that means that the whole method breaks down. And here is an interesting thought. So take this, now I'm hand waving, okay? This was the proof for q smaller than 2. I'm going to explain to you, try to give you an intuition what needs to be done for q larger than 2, but I'm not going to do it rigorously. So here now it's just trying to give you hints of what is happening. Take a box of size, say, n over 2. and look at the probabilities that this guy is connected in the random cluster model. So you take phi 0, and let's say this is the upper half plane H, and look at 0 connected to distance n over 2, or n, or n over 2. Well, physics predicts that this should behave, and you saw that also with the percolation model. This decays like a polynomial. And in fact, what you expect is that these guys really behave like a polynomial, that there is an exponent alpha, which I'm going to call alpha q pi, and I'm going to tell you why, plus e to the power of 1. You really expect that. I mean, from now, it's just expectation. Again, I'm just conjecturing things. I call it alpha q pi because here I have an opening of pi. Okay, if you look at that, what is if I take a point, let's say if I take this point, a point which is not too close to the borders, to the corners, this guy, how much do you expect? I mean, what should be the probability that this guy is connected to this guy? Well, this guy should be connected to distance n over 2. This guy should be connected to distance n over 2. And if they are both connected to distance n over 2, they have no reason a priori to be connected together. But the Rousseau-Semmelweis theory tells you that, okay, with positive constants, you are going to actually manage to glue these two guys together. So in fact, if I look at this term, what is the right prediction for the order of magnitude of this? Well, it should be, so the sum for x in the boundary of Rn of phi 0 Rn Pc Q, and here I'm lambda n, sorry, of 0 connected to x. Well, if I ignore the problem of the corners, and trust me, you can ignore them, it's not at all a difficulty, it should behave like, well, there is roughly n guys on the boundary, and each one is connected with probability 2, I mean, 1 over n to the 2 alpha of q pi. So this is a right estimate. Maybe I went too fast. It's n times n to the minus 2 alpha q pi plus e to the power of 1. Okay? N guys, probability for each guy is roughly that. So this thing is going to remain bounded away from 0 if and only if alpha q pi is smaller or equal to a half. And alpha q pi, oh man, I forgot my, okay, I don't remember by heart the expression, but alpha q pi is smaller than a half if and only if q is smaller or equal to 2. You can predict what is the value of alpha q pi using, for instance, the SLE technology, whatever. The important thing is that the prediction is actually that this quantity is going to tend to 0, not this one, but this one is going to tend to 0 for q larger than a half. Okay, I mean, something q, 2. It's true that anyway, you do not care so much because you don't need this sum to be bounded away from 0 to have an infinite expectation. You would only need that it doesn't tend to 0 too fast. And in fact, you can prove that alpha q pi, you can predict that alpha q pi is always smaller or equal to 1. So it would tell you that in fact this sum is always larger or equal to 1 over n. So if you sum on everybody, you should always get something diverging. The only problem is that it's not, okay, this is true, but just the method breaks down. As soon as this thing becomes negative, I'm telling you that in fact this big sum is going to converge exactly to this, and determining the speed is going to be very difficult. You cannot do it like that. So that's where I was stuck on that until I realized that conformal invariance, the prediction of conformal invariance really helps you a lot. Because imagine I do the same computation in a different geometry. Imagine I do the computation in this geometry. I put 0 here, and I look at a slit domain somehow. I just remove one slit going up. And I do exactly the same computation. So this is, it's removed. Okay, so So I do the same computation on the contour like that, going like that. And I could hope there that when I look at the expected number of guys here connected to here, that I get basically something bounded away from 0. What would be the prediction for this guy? For this guy, what you would look at is there will be, you take a slit domain S, so you take a domain S like that, and you look, the probability that 0 is connected to distance n here should behave like 1 over n to the alpha q 2 pi plus little o of 1, because now the opening is 2 pi. And here conformal invariance is beautiful, because conformal invariance allows you to predict what is this alpha q2 pi in terms of alpha q pi. The fact that there is a mapping between edge and S, which is square, sorry, because there is this mapping, in fact, you can predict very easily that alpha q pi, 2 pi has to be 1/2 of alpha q pi. So alpha q 2 pi should be 1/2 of alpha q pi. That's once again just a prediction, it's not a proof. But then when you do the computation, what is going to be the term you get here? Well, you need this guy, let's say this guy is not on the corner, so it's here. So it needs to be connected to distance n over 2 on something that looks flat. So you are going to get n to the minus alpha q pi. But this guy, to be connected to distance n over 2, is going to be alpha q 2 pi. And you have n terms. So when you look at this sum in this domain, this different domain, you expect this. So you expect that it behaves like n to the 1 minus 3/2 of alpha q pi plus little o of 1. So now you only need alpha q pi to be smaller than 2/3 in order to have that this sum on the boundary is going to remain bounded away from 0. And this tells you that alpha q pi is smaller than 2/3 if and only if q is smaller or equal to 3. So maybe up to 3, if I work in this geometry, I'm going to manage to do the thing. And it's exactly because all of this was only predictions. But if you take this geometry, if you look at this guy with a slit domain, you do exactly the same reasoning. What you're going to get is that the sum of the terms on these things, so the things that are close, the equivalent of C1 plus and C1 minus, they contribute positively. The sum, the costs that we have here, when you compute it there, you get that it contributes positively. So you get that the sum of these guys on the boundary of this guy of the probability of being connected is larger than a constant. And if you use the comparison between boundary conditions, you can deduce exactly as before that the sum on the guys on the boundary is larger than a constant. So in this case, you can sum on everybody and you finish. The problem is, it's only q smaller or equal to 3. Well, now, I mean, there is no, you start to see where I'm heading. If I take an opening which is larger than 2 pi, take 4 pi, 10 pi, what does it boil down to? It's just that it's a slit domain. Now it's not a planar domain anymore. It goes around the origin, you know, like in a parking lot, for a certain number of layers. You do the same reasoning and it's going to work. For any q smaller than 4, because I have that, for any q smaller than 4, strictly, I can find a large enough opening so that I'm going to choose the opening in such a way that here, if I take 2k pi, or k pi, I'm going to get that this guy is 1 over k alpha of q pi. So for any q smaller than 4, this guy is strictly smaller than 1, so I can choose a k in such a way that this thing is going to be smaller than 1. And if I do the reasoning in this non-planar guy, I'm going to get also that the integral along the points that are far away from the axis is constant. I mean, is larger than a constant. The difficulty there is that now I'm not planar anymore, so I cannot just do comparison between boundary conditions to go back to the plane. Here, and in this case, it was. In the other case, you need to work much more, but you can do it. Remains the q equal 4, for which alpha of q pi is exactly equal to 1, and in this case, you need to take the universal cover, in fact, of the plane minus a point. So you really need to take something infinite. But I think it's kind of a very cute thing that, you know, just looking at conformal invariance, you can somehow predict some kind of strange geometry in which your argument is going to work. Because after, the argument doesn't use conformal invariance at all, because we do not know conformal invariance of the model. And in particular, I like this work on the universal cover, because you are going to see in particular in the class of David in the second term with Dimers and Ising that statistical physics on discrete Riemann surfaces is a very interesting thing. You have a lot of topological terms that enter into the game. You are going to see that you can work on the torus. Maybe you will even look at more complicated geometries. But somehow, geometries with a singularity, a logarithmic singularity like that at the origin, were not studied. And here it's very useful. And I think it's the first appearance of that. I didn't see that in any other context, and it will be very interesting to see a little bit more how you do, because, I mean, the difficulty is you can study things like that, but then you need to bootstrap your information to the plane, and this is something which is, in general, not obvious. And for instance, for self-avoiding walk, I have a very, very cute argument to try to prove that you have polynomial corrections for the number of self-avoiding walk using this universal cover. And unfortunately, there is just one very simple property that I was certain was completely obvious when I even wrote the article, and then realized that this stupid property, I don't know how to prove it. So somehow we know very little on how to go from, if people are interested, by the way, they can try. So if you take the universal cover, how do you study the properties of this universal cover, and how do you relate them to the model on the plane? So this is the end of this chapter, and in the end of really a part of no, it's not the end of this chapter. So next week I'm going to mention a little bit what happens at q equal 2, but this will actually be one of the big things you are going to do in the second term. So it's going to be to say that at this value we know how to prove conformal invariance. So I'm not going to prove conformal invariance, but I'm going to tell you a little bit about it still. And this will be for next week. And then it will remain something like 3 or 4 classes where we are going to switch completely and look at a completely different geometric representation, which is called the random current representation, and prove a lot of cool stuff on the Ising model, because it will be specific to Ising. Okay, so next week.